Welcome 2200. We're going to do experiment 1 together and I'll be your lab partner. What I'll do is just simply read the lab manual and do what the author instructs us to do with little commentary. The reason I say that is because I've made videos for the rest of the labs in your semester, and on those I elaborate on the equipment, how to set it up, I comment on the measurements that we're making, and those involve a lot of analysis. This one, however, is qualitative, or takes on a qualitative approach where you're kind of exploring the nature of electrostatics and in the process getting shocked. Well, that means I'll be getting shocked, but it's by far the funnest lab for the students in this course, from what I've seen anyway. Probably because, you know, it's more laid back, you're not taking home a bunch of data to analyze. Like I said, you're just exploring. So I will do what is outlined in the lab manual. You'll watch, follow along, and there are some questions that need to be addressed, and after watching the video, you should be able to answer them. So the equipment is set up. Let me turn the camera around and we'll get started. Okay, so this is for part A, corona discharge. I will bring the blade of the screwdriver closer to the Van de Graaff and observe what happens. Want to hit the light? So the screwdriver is getting charged and it's jumping across the handle into my hand, so it doesn't feel very good, but you can see the blade of the screwdriver near the Van de Graaff. Actually, want to zoom in on that? So, there you go. Corona discharge. Part C, electrostatic repulsion. That is tissue paper there, cut into streamers, and they're taped to the, not directly on top, but like 3/4 of the way up. This view is to show that they are normal to the surface, except for like 3 of them. They seem to be stuck together. So I'm going to shut off the Van de Graaff. And see how long it takes to discharge. So let's see what happens when I touch the Van de Graaff. So you should be able to explain that phenomena. So here's the other part of part C, and what your lab manual makes reference to is a plastic container with 2 metal caps. So that plastic container, as instructed in your lab manual, is to be placed right here on top of the Van de Graaff. We don't use that old model anymore. We have that heavy duty container here. And the other one just wasn't too conducive to the lab. It would fall off, they break. This one here is heavy duty, plus it does not sit on top of the Van de Graaff. It gets charged, but in a different fashion, and I suppose that would be your job to explain how. Now, that can be placed either on a desktop or on top of this blue base of the Van de Graaff. Now it works best when it is indeed on top of this blue base, and it works best placed on top of that base because the base is grounded. So when it's totally off, you have no motion of those pit balls. Now crank it back up. That's to give you a better view of the equipment or how that container is designed so that you can explain how it works. Okay, so this is for part D. Now, your lab manual instructs you to use this transfer wand. You charge the end of this ball on the Van de Graaff and then touch the ping pong ball with it. And you get shocked. The reason I don't use this is because it's pretty difficult to get them in that configuration. They start bouncing around, and it's like you charge one first, so that gives it a negative charge while the other one is positive, so they attract to one another and start bouncing all over the place. Anyway, they're just hung directly above the Van de Graaff, and you get this nice steady state, and you are to figure out how much charge each ball has on it. And you can do that, of course, by knowing how far they are apart. What I did was I put a protractor up above, so the ribbon on the left is reading 81 degrees. The one on the right is reading 101 degrees. The length of that red ribbon that it's suspended on, from top to bottom, this length is 20.0 centimeters. Now, when I weighed the masses of the balls, I weighed them both together. Both together, they are 6.17 grams. So one ball would just weigh half that. The only other information you would need is the diameter of the ball, and I'll measure that and get that to you. So again, for part D, you want to determine how much charge each ball has in this configuration here. And that is it for part D. By the way, you can see it doesn't take long for them to discharge. Okay, good luck on that analysis. Okay, so this isn't in your lab manual, but it's a few things you might want to consider. What I'm going to do is get this conductor and bring it in close proximity to the Van de Graaff. And in doing so, there's going to be an arc. But pay attention to the distance in which I have to bring this conductor to the Van de Graaff. Now I'm going to ground this conductor. grounded. So this here is ungrounded. And this here is grounded. So whether or not it's grounded or not, you're getting the same effect, except the distance is involved and perhaps the intensity. So the last thing is to insert this crown of thorns, which is nothing more than a bunch of pins. And I'm going to put that on top of the Van de Graaff. I'm placing Play-Doh on it just so that it doesn't fall off, because this will be vibrating when I turn it on. And I want to see if that produces a different effect. Ungrounded. Obviously it has to be much closer. Grounded. Slightly farther away, but still closer than the other case. So it'd be interesting if you guys could explain the effects or why the crown of thorns has a significant effect on the distance this conductor needs to be placed to the Van de Graaff for there to be a discharge. And that's it for this lab.